In previous lessons, we discussed the idea of finding relative extrema by using the first derivative test. We also talked about the idea of concavity and how we could use the second derivative to determine where a function is concave up and concave down. What we're going to do today is we're going to put those two ideas together and we're going to develop another test for locating extrema. And it's going to use both the first and the second derivative. It's called the second derivative test. So the second derivative test says let f be a function such that the second derivative of f exists on an open interval containing c. If the derivative of c is equal to 0 and the second derivative is greater than 0, then what can we determine about that point? So let's see if we can kind of sketch what that would look like. If the derivative at the point C is equal to 0, then we know we have a horizontal tangent line at that point. We have a critical number at that point. But if we also know that the second derivative at that point is greater than 0, then we know that the graph would have to be concave up. So if we know we have a horizontal tangent line, and we know that the graph has to be concave up, we have a point with a horizontal tangent line and a graph that is defined and concave up. If we put those two ideas together, then that means that that point must be a relative minimum. Likewise, if we know the derivative is equal to 0 at that point, and we know that the second derivative is negative, is less than 0, then again we have a point with the horizontal tangent line. But this time we know that at that point the graph must be concave down. Well, the only way that that could happen is if that point is a relative maximum. So we can put the idea of having a critical number, specifically a point where the derivative is 0, a horizontal tangent line, and knowing something about the concavity, we put those two ideas together, we can still determine whether or not we have a relative maximum or a relative minimum. If we don't know the sign of the second derivative, or if the second derivative is equal to 0, we don't know anything about the concavity. So in that situation, we would not be able to use the second derivative test. We would have to go back to the first derivative test and check the sign of the first derivative on either side of that value, and that would let us know whether or not it was a maximum, a minimum, or neither. So let's check out an example. We're going to use the second derivative test to find the extrema of f of x. And we have the f of x is equal to negative 3x to the fifth plus 5x cubed. In this problem, we need both the first and the second derivative. So we're going to start with our first derivative. F prime of x is equal to, well, we'd have negative 15x to the fourth plus 15x squared. There's nowhere where our derivative would not exist. So here our critical numbers would just simply be where this is equal to 0. And to solve that, we could factor out a 15 and an x squared. That's going to leave me with a negative x squared plus 1. So either 15x squared is equal to 0, or I'm going to rearrange this, 1 minus x squared is equal to 0. I'm just switching those terms around. If 15x squared equals 0, then that means that x squared has to be equal to 0, so x would have to be 0. If 1 minus x squared equals 0, that means that x squared would be equal to 1. So if I take the square root, I get that x could be positive or negative 1. So here we have three values, three places where the first derivative is equal to 0. And what we want to know is, what does the sign of the second derivative look like at each of these points? So I need to find the second derivative. I have the derivative of negative 15x to the fourth will be negative 60 x to the third, plus the derivative of 15x squared would be 30x. And we don't necessarily have to factor this, but it might make it a little bit easier. I'm going to go ahead and factor out the negative just so that my leading coefficient is positive. They both have a factor of 30, and they both have a factor of x. So if I divide this by negative 30, I get 2. If I divide that by x, I have x squared. And if I divide this by negative 30, I'm going to get negative 1. If I divide by x, then the x's will cancel out. So now I have my second derivative, and I want to know, what is the sign of the second derivative at each of these values? So I'm going to start with x equals 1. At x equals 1, the second derivative at 1, again, I don't need to know the exact value per se. I just need to know if it's greater than 0 or less than 0, if it's going to be a positive or a negative number. So if I put in 1 here, I'm going to have a negative number times a positive number. So at 1, the derivative is going to be negative times positive. It'll be negative or less than 0. So then we know that f prime is equal to 0. The second derivative is negative, which means the graph is concave down. So we know that we have a relative maximum at this point. At the point where x equals 1. And if we plug that 1 back into our original equation, we would have negative 3 plus 5 gives us 2. So we have a relative maximum at the point 1, 2. Now we're going to repeat that process with negative 1. Again, I don't necessarily have to know the exact value of the second derivative at negative 1. I just need to know if it's positive or negative or 0. So if I put in negative 1, then I'm going to have negative 30 times negative 1 is a positive. When I square my negative 1, that's going to make this term positive. So now I have a positive value times another positive value is going to give me a positive value. So it's greater than 0. So now I have a horizontal tangent line, and I know my graph is concave up. That tells me that I must have a relative minimum at that point. Where x is negative 1. If I plug negative 1 in, I've got negative 3 times negative 1 is going to give me a positive 3. And then 5 times negative 1 will be a negative 5. So positive 3 minus 5 will be a negative 2. And finally, I need to check my other point, which was at x equals 0. So at x equals 0, if I look at the second derivative at 0, I would have 0 and so 0 times whatever I get here is just going to be 0. So the second derivative here is actually equal to 0, which doesn't tell me anything about the concavity. So here, our test fails, which means that we need to go back to our first derivative test. So I want to look on either side of 0, but I want to make sure that I don't go past negative 1 and positive 1, because I've already determined I have a relative maximum or minimum there. So if I look at a value between 0 and negative 1, looking at my first derivative, I'm going to have a positive number times a positive number. It's going to give me a positive. If I plug in a value between 0 and +1, I'm going to have a positive number times a positive number, which tells me that my function is increasing, and then after 0, it will continue to increase. So we don't have either maximum or a minimum at this point. So we have a relative maximum at 1, 2. We have a relative minimum at -1, -2. And we don't have a maximum or a minimum at 0 because we don't change from increasing to decreasing or decreasing to increasing. In the next example, we're looking for the extrema of f of x equals -2 cosine x minus x. I'm going to add some restrictions to this. We're just looking for the extrema on the closed interval from 0 to 2 pi. So I'd like for you guys to take a few minutes to see if you can use the second derivative test to determine if b has any and what kind of relative extrema it has on the closed interval from 0 to 2 pi. Once you have the problem worked out, then you guys can start part 2.